Hi, and welcome to MATH3411 Problem 9, in which we'll be looking at the ISBN code, or more particularly the ISBN 10 code. It's the code consisting of all of the sequences like this, the code word there being equal to x1 up to x10, where each of these is one of these here. It's one of the decimal numbers, 0, 1, 2 up to 9, and also 10, which we write as an x. And we're only choosing the sequences that satisfy this particular condition here, that if you take each index from 1 to 10 and multiply it with the value x1 to x10 pairwise, add them together, reduce modulo 11, then you get 0. So this is a checksum, a type of slightly complicated checksum condition that the ISBN code has. Now, the first thing that we should address is, why do we use these codes? And they've been around for quite a while, the International Standard Book Number, so they're about codifying, or rather giving a unique code to books. And these days we're using the ISBN 13, so we're adding 3 more digits, but this was valid and still in use today for quite a while. So if you have a book, you want to give it a unique identifier, or one of these code words to say which book is it we've got. And that's of course useful if you've got books, if you have libraries, if you're a librarian, or if you want to go look some book up and make sure that you're keeping track of your references or whatever. So this is not a code meant for a lot of information, it's just occasional information which says something about books, particular books. And there are some more details which we'll skip in this example or this problem. There are chunks of these digits here, or 11 digits if you want, that make this code user-friendly. In particular, some of these digits say precisely which country and region and so forth, which topic we're talking about. We'll ignore those details for now and just look at a simplified model. So, given that we don't need this code for a lot of communication, a lot of sending data through some noisy channel type protection, all we need here is for it to be user-friendly, and we don't really need any error correction. We just want this property here, that the code can detect one error and also detect when we're swapping 2 digits around. And you might see that that's useful, for instance, back in the day where you might be a librarian writing down the ISBNs of books and maybe make a typo. One of these might be wrong, or you might swap a digit by mistake. They're easy mistakes to make, but then this code would pick up on that mistake and say, hey, this is a wrong ISBN, could you please go back and check it? So there wouldn't be any correcting, but there would be that detection, which would be useful in that case. These days maybe that's not so important. Detecting one error we could get if we simplified that checksum, got rid of that I and simply just added the digits together. So that would be more similar to the ASCII codes or other things with checksums of a very simple kind. You just reduce them mod 11 in this case, but if it were binary code words, you'd reduce them just mod 2. The reason that we have this slightly more complicated sum there is that we also want this nice condition for digit swapping. The fact that this sort of code does actually allow detection of an error and digit swaps, we've seen in the lectures and the lecture notes, but instead today we'll be proving some of it. We'll be looking at the detection here and upgrading it in a certain way, and that certain way is as follows. We're going to take this code and upgrade it to not only detect one error but correct one error. So here's what we're going to do. We could say the new code, the ISBN plus if you want, is going to be a new code, let's call it C+, of the same sort of format, except now we're not only going to have this condition, we'll add another condition which will be more restrictive but allow us to upgrade that detection to correction. And the condition that we want is sort of like this, except it's just simply the natural checksum condition. You just take all of the digits there and add them together. I think in the problem itself we were restricted to the numbers from 0 to 9 and not the x there, but that's an irrelevant detail for now. It actually sort of makes better sense to have the 10 in it for these purposes. Oh yeah, we can now upgrade the detection to correction, so let's do that. And correct. So now I claim that this code can correct one error and detect a digit swap. And that's what we actually have to show. So now I'm going to be a bit lazy here. By the way, I've already been a bit lazy because the first part of this question asked you to estimate how big this code was. I'll let you do that. It's sort of a fun, heuristical game. There are several answers, and I'll leave that as a challenge to you. But here in part B, show that this code here can correct one error and also detect a digit swap. Well, here I'm going to be lazy once again and say the detection of digit swaps is exactly the same for just the usual ISBN, and the proof is in the notes and the slides. So have a look at that and try to understand it and maybe reproduce it yourself. That would be good. So we're going to focus on the correction of one error. So let's have a look at what's going on. So we might have two people here. So here's a person, happy person, and here's another person, also happy. And this person there shouts out a ISBN plus code word if you want. So code word X there, and then it goes through the air there and might get corrupted a little bit, and the receiver over there might hear it as something else. Let's get a black pen here just to signify that it might not be the same as the sent message. So we've got over here, we've got sent. That was the code word, the ISBN plus if you want. 10 digits there, satisfying those two congruence equations. And then we've got received. Oh, this is a rather more visible pen. Here we go. Y, and we have a Y there, not an X. So Y1. And like so. And let's assume that there's exactly one error here. And that error is in some position. Let's call it the kth position there. So these two words here, the code word that was sent and the word that was received, they're exactly the same in all of the coordinates except exactly one coordinate where we have one error here. So error. Okay, now if we want to show that we can correct one error, then we need to do two things. We need to figure out where the error is, in other words the value of k, and we also need to figure out the difference between x and y, so how much they differ, and then we can use that to correct. So that's all we need to do, so let's do that. Okay, well, we can use what we've got here, so let's do that. We can start off with the first sum there, but let's look at the received messages. So with that person there, we've received that word with one error in it, and that's all the information we have. So we have to use the information there, which is here, somehow to correct this. So let's look at this sum here. And here I'm just going to be a little bit lazy and just use green. So let's add the black or the y elements together. Now all of them are the same as the x's except for that one there. So if we're adding all of these y's together, we get that that's the same as the x's for all the indices not equal to k, and then we have that one here, yk. Okay, now we want to make that sum equal to that sum because that's congruent to 0, and then things will cancel out. So let's add the missing term here, the xk, and then quickly subtract it, so as not to break mathematics, so to speak. So we want this sum there, where we're indexing over all the i's, so we can leave it invisible, and we can do that by subtracting quickly that term that we've added there, and now we just have yk, and Because of this condition here, then this sum is congruent to 0 mod 11. So we just end up with these terms, and let's just turn them around to make it neater. Yk minus xk mod 11, and there we go. Okay, well, that's cool actually, because now we know the difference between the received kth coordinate and the sent kth coordinate, and that's exactly what we need in order to adjust the error. And that difference there, that's given by the sum of the y's, which we do know as the receiver. What we don't know is the value of k. In other words, we don't know where the error is, but once we know that, then we can correct it using that difference. So let's find the value of k. That's using the second condition, that this complicated sum is 0. So let's have a look. So we've got this complicated sum of I and now y. Let's see whether that might lead to something. Well, again, all of the yi's are the same as the xi's, except in the kth position. So this is exactly the same sort of thing as above. We've got that we have the same terms here, except now we're just adding I, or multiplying I here and k there. Otherwise it's exactly the same. Here we want a sum of the form over I times xi for all the i's from 1 to 10. We can do that by adding the missing term, the kth term there, and then quickly subtracting it again. So that would be minus k xk, and then we have kyk, kyk, and we can write that as, well, again, we've got that this is congruent to 0 by the condition that we have up here. All of the x's form a code word and therefore satisfy those conditions. And so that cancels out, and then we can tidy this up by writing, no, that was ugly, let's write it a bit neater by writing k outside the brackets and then yk minus xk, and all of this is still mod 11. Okay, so to speak. Why is that great? Well, it's great because now we actually know what the value of k is. Why is that? Well, we can divide by the difference here, divide this by the difference, and we'll get exactly what we want. So k is equal to, well, this sum here, which we can calculate as the person receiving the message, then times the inverse of that difference. Now, since we're working modular 11, we know that there is a inverse value to this because, well, for one thing, this is not 0. If these two were the same, then there wouldn't be an error. And for the second thing, we're working over the numbers mod 11. So if we're talking about non-zero elements mod 11 or numbers modular 11, we know that there's always going to be an inverse because 11 is prime. We'll get to that later in the course, by the way, if you're still a little bit shaky about modular arithmetic. Okay, but here we have a formula for k involving things that we can calculate as the receiver. And here no, that's correct. I should not correct something that's correct. So, using the first equation, just the sum of the y's, we can find the difference there. That's what we'll use to correct the error if we know where it is. And now we know where it is because k is exactly equal to that weighted sum times the inverse of that difference, and there we go. Maybe looks a little bit complicated, but it's not actually too hard. And in fact, we're going to do this right now with part C, where we actually have to correct a code word. So let's have a look at that. Okay, so here in part C we have to correct this particular received word under the assumption that there's exactly one error. So what do? Well, we need to figure out where the error is. That's the value k there. And we also need to know how to correct the error, and we can see that by finding out what the difference here is. Now, if we're talking about a binary code, then we wouldn't actually need to figure out that distance because it would automatically be 1. If you're sending a 0, then the error would be 1, and vice versa. But if you're dealing with a bigger number system like the ternary system or quaternary, or in this case a number system with 11 in it, well, then we need to know exactly how much we have to adjust in order to correct the error. So let's have a look here. We need to do two things using the formulas that we found just previously in the proof. So first, we have to calculate this difference here, xy minus yk minus xk, and that's the sum of all of these y's here. So we just add them together, reduce mod 11, and I like to, well, you can do this in two ways, or several ways. You could add them all together, get a number, reduce it mod 11, or you could reduce things as you go along to make the calculations just a little bit easier if you're doing it by pen and paper or in your head. So anyway, let's have a look. 6 plus 8 is 14, 16, 23, 24, 27, 35, 40, 40 reduced mod 11 is minus 4, or 7 if you want. So where is that? So 7 for instance, or minus 4. Now the reason that I'm using both of these, or writing up both of these, is that when we do correct and figure out what that value there, xk, is equal to, then we want it to be a positive value, not a negative value, just so that it fits the parameters of the code. Okay, we've done the first thing. That was easy. We found the difference there. Now we need to do the second thing, which is to find the value of k, and that tells us exactly where the error is. So let's do that. That's a little bit trickier. K is equal to, well, that weighted sum there times the inverse of what we found here, this difference. So we need to do two things first. We need to find that weighted sum, then we need to find the inverse of that difference, multiply them together, and finally when we've done that, then we can figure out what and where the error is and correct it. So let's look at this weighted sum first. That's these numbers here, multiplied by the coordinate values 1, 2, 3, and so on. And then we need to take each of these pairs, multiply them together, and then add them up and reduce mod 11. So here, for instance, 0 times 1 is 0, and this 6 plus 2 is 12. Now you can just do that immediately and then reduce mod 11 afterwards, but I like to just reduce as I go along. That's a little bit quicker for me at least. So 12 is the same as 1, 24, 8 times 3, that's the same as 2, we have a 0 there, minus 1, 42 is the same as minus 2, 1 times 7 is 7, or minus 4, 24 is plus 2, 72 is minus 5, and finally we have 50, which is plus 6. Okay, what do we have here? We have some cancellations, 2 and minus 2, 1 and minus 1, okay, and then we've only got these numbers there. We've got 2 plus 6 is 8, minus 9 is minus 1, and we can write minus 1, or we could write 10 if you wanted to, but either is fine for now. So let's have a look. K is congruent to minus 1 times, and then we've got to find out the inverse of that difference there, which was equal to 7 or minus 4. So here, to find the inverse, you could either use the Euclidean algorithm backwards and forwards, but that's a little bit overkill in this case where we're dealing with small numbers, and in particular small modulus, which is just 11. So let's just look at the multiples of 7, 7, 14, 21, and so forth. Hey, 21. Let's write it somewhere here. So that was 3 times 7. And the reason that I said, hey, was that 21 was very close to a multiple of 11. So it's 21, which is exactly congruent to minus 1 mod 11. And what we wanted was to find some number times 7 that was equal to 1. And we can do that by just putting a minus in front of the 3. So now we've got minus 3 times 7, that's minus 21. And now that's a plus 1. So in other words, we've found the inverse of 7. So the inverse of 7, that's equal to minus 3 mod 11, or also equal to 8 as you want. But actually minus 3 is not bad here. So we've got that the inverse of this difference here is in fact equal to minus 3. And so k is equal to 3 mod 11, and in fact 3 because this is the position of the error and it has to be a positive number between 1 and 10, which it of course is. So that seems to work out. Now we've got everything that we need. We know where the error is, so let's have a look at that. The error is in the third position here. And now we need to figure out what exactly that corrects to. So there we have to say, well, we've got the so if we want to write it up here, this would be x, the third x, and the third y, and we're wanting to try to figure out what that x3 is equal to. So let's see. Well, we've got that this difference here is equal to 7, so if we rewrite that a little bit, so x3, or that's our xk, is equal to, well, the yk, or y3, and then we have to subtract the 7, or add the, or subtract the -4, so to speak, or add the 4, but do one of those things so that we get a value that when we subtract it, or from 8, gives us a value between 0 and 10. So let's see what that's equal to, and then we can maybe modify the 7 if we get something outside of the bounds. So that's equal to 8 minus 7, which is 1. Yay! The corrected value here is indeed within the bounds from 0 to 10, so to speak. So that's the value that we want. Otherwise, we'd have to choose something else from 7. Could be the -4, for instance, and so on. So we've corrected this value here, and indeed that gives us the sent message, which was x being equal to everything there, 0, 6, and I'll skip that part from now and just write up all the rest. And then of course we had the corrected value, which I'll draw a little box there, and that was equal to 1. So let's write that there, and that indeed is in fact the answer. We have in fact in real life corrected this sort of enhanced ISBN, and that's the end of the problem. Thank you very much.